So LSTM stands for long-term, short-term, long short-term memory. Okay. Using a lot of formulas, using a lot of theory, what LSTM does is when you are predicting this, what it'll try to do is it'll try to keep the right information in the memory. There is a new cell state. Until now, there is only hidden layer. There is that is known as hidden state. There is something new, something called a cell state that will be introduced. So important information will be kept for long duration. For long duration, important information will be kept. Unnecessary information will be dropped and failed. Unnecessary information will be dropped. That means when you are predicting this, automatically we'll ignore some words. We'll keep the words that are important. And this prediction will be based on the words that are related to this. So the main idea behind LSTM is we may want to ignore or forget few intermediate inputs. We may have to forget some information. We may have to keep some specific words or specific information that is for a long interval. Let's say if you have mentioned, I live in Bangalore, or if you have mentioned, I am traveling to New York. After a lot of sentences, you're talking something about New York. Then somewhere that was mentioned long back, that need to be kept, that need to be used for the prediction of the next word. How is that achieved? Using a lot of formulas. So until now we have only hidden state or the hidden node. Now a new state, cell state, is introduced. In that cell state, previous cell state, we forget some information and the current input is added to it. And then like there is something called forget gate, there is something called input gate, there is something called output gate that is added. So there is a lot of formulas that have been added. There are several weights that are added. This is a cell state that is new. Apart from that, forget gate, output gate, input gate, all these are added. These formulas will make sure that finally we have the information, whatever is the information that need to be forgotten or ignored, that will be ignored using the forget gate and its corresponding weights. Whatever the new information that is given as input, that will all be carried through these input gate related weights. What is the output that we need to give it? That also be given using output gate weights. Then the actual time step, cell state, and all these are added to make sure that we have the final output eventually that contributes to long-term memory. Understanding these formulas will be very tedious and very difficult. In fact, LSTM in itself is one of the most advanced way of predicting the sequential or handling the sequential data. We'll try to get an intuition. We may not be able to get an idea on or completely understand these formulas. At least if we get the intuition, then when we are using LSTM, then we can get the right understanding of it. So the usual RNN model, if you take RNN, you have input layer, hidden layer, output layer, input layer, hidden layer, output layer, and the previous hidden is connected to next hidden, is connected to next hidden, next hidden. This is the RNN. The blue one is RNN. Do you agree? If you ignore this orange amber color, if you take only blue one, these hidden is nothing but hidden nodes. These are some hidden nodes. These are some hidden nodes. These are some hidden nodes, isn't it? These are some hidden nodes. This is the RNN, which is short-term memory. Usual RNN that we already know. This takes care of short-term memory. That means it will automatically take care of if you are predicting the 10th word or if you are predicting the 50th word, the last 10 words will be used in predicting the next word mostly. That it will do a good job. However, long-term memory is something that we want to carry forward. That is why new state is added, which is known as cell state, which is also nodes only, just like hidden nodes. You have the new state, but the cell state is calculated slightly differently. Let us see how to update this cell state. Hidden nodes, we already know how these are calculated, etc. But how this cell state is added, let us see. Okay. This whole thing, cell state, hidden nodes, is put together is known as LSTM cell. This is known as one LSTM cell. And what happens in an LSTM cell, we'll try to get an idea on these formulas. So what we do is current input. Look at this, all of you. I'm trying to explain the LSTM formulas. So you have the current input, which is some nodes, and the previous hidden output. That also some nodes only. We have already seen this in the previous example. 139 nodes here, 10 nodes here put together, okay, will become 149 nodes. You remember that, right? So that is the current input plus previous hidden output. Okay. First, what we do, we take a copy of this. This is a copy. And then cell state is nothing but in the beginning, cell state is, there is no cell state. It is completely blank. If we keep on going in the sequence, this cell state keeps on updating. So as of now, this cell state is having some nodes. Maybe they may not carry any information in the beginning, but right now they have some information. We take a copy of this current input and previous hidden. We multiply with the cell state. We multiply with the previous cell state. When you multiply it, you may erase some information, which means that contributes to the forget gate. That means we are updating the cell state C t minus 1 previous cell state. We are multiplying that with the current cell state, current input and the hidden node. So we are taking this output, we are taking a copy of this and then multiplying with this. By doing so, we might be erasing some information that is not required. How do you decide that? How do you decide which information need to be avoided? That need to be done based on the training data. So training data will be taken care of it. So we will be giving the weights. So based on these weights, that information that need to be forgotten, that will be erased. That means from cell state, some information will be erased. Cell state will be updated. That is only part one. Part two, we take another copy of this. We take another copy of this. This is one copy. Cell state is updated. Another copy of this, what we will do is we will append the information of this current input and the previous hidden output. We will append some information to the cell state. Here we are erasing some information that is unnecessary based on the data, based on the training data. Based on the training data, we are appending, we are adding some information to the cell state. Basically, we removed whatever is unnecessary information from the current cell state. From the cell state, we removed some info. Now we are adding some info based on what you are adding, based on the current input, based on the previous output. What need to be added will be decided based on the data. This is known as input gate. Previous one is forget gate. First you apply forget gate, then your cell state will be updated. That means something will be forgotten, something will be erased from the cell state. Now you add the extra additional information using the input gate. The last one is output gate. What need to be, until now I have shown whatever is the previous hidden state output, current input, that will be given to the next hidden state. Until now, that is the short term memory thing. That is the usual RNN model. However, what we will do is we will not take a complete copy of this. Based on the current cell state, we will not give the exact input. This output should not be given as exact input. What we have to do is based on the current cell state updated, like after whatever is removed, that has been removed, whatever is added, that has been added, based on the current cell state, based on the current input, based on the previous output, what need to be given as exactly taken out of this, what need to be taken out of this, what need to be carried forward, that will also be decided based on the cell state. That will be given as the this output. This will be decided based on the output gate. Those are all the formulas that are coming up actually. The forget gate formula. This is the formula for forget gate. That will update the, this is the formula for cell state updating. That means applied forget gate on this. After that, this is the formula for input gate. After that, what are you doing? You are adding the input information. This is the formula for output gate. What are you doing? You are taking this cell state into output. That will give you, basically this output is not directly from here. This is based on the cell state. Even after going through this cell and all that, this looks like even more confusing rather than adding the clarity, especially when we see these formulas, especially when we see these diagrams of LSTM. It looks very confusing rather than adding the clarity. So that is why, to get the clarity, what we can do is we will take an example and try to get the analogy. I do agree that these formulas are not that easy to follow. Let us take an example. Let's suppose Jim is a software engineer. He works for an IT company. Linda is a teacher. And what is the next word? This is what I want to predict. You want to predict what is the next word. Obviously, you had to take information from here, 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 here. You have to take a lot of info, and this current next word may depend on any of these or maybe previous ones also. Okay. So what is the next word? If we are using LSTM, how LSTM works and gives us the prediction about the next word. Okay. Historically, these are the training data examples. How do you give the training data? Maybe you can train on a novel. Let's say if we take Shakespeare's novel, and if we train on Shakespeare's novel, and you wrote 4 words, whatever is the next immediate word written by Shakespeare historically, that will be predicted. That means we can train on a Shakespeare's novel and we can write like Shakespeare. We can generate text like Shakespeare. Like that, let us suppose this is one of the novel, and these are some of the previous training examples, historical data. I'm showing you few examples. Here are the examples. Linda was late that day. She apologized. Linda's alarm goes off at 5 a.m. Her day starts with a cup of coffee. Jim told Linda, "You have such beautiful eyes." Linda smiled at him. She continued to walk. Linda is a teacher. She has 6 years of experience. Linda likes exploring new cities. She traveled to Paris last month. Linda got promotion last month. She got good pay hike. These are some of the examples from this novel. Based on these examples, we are asking LSTM, can you predict the next word? Okay. You can imagine this particular cell state as a box that is carrying the subject of the discussion. Okay. You can imagine the cell state in LSTM as a particular box that is carrying the subject. It will not only carry the subject, it will carry the subject, it will carry the city. City need to be carried for a long duration, right? It will carry the year, it will carry the month, it will carry a lot of information that need to be carried for a long duration. Right now, for our example sake, imagine this is carrying the subject of the discussion. All of you, are you with me? How LSTM works. Now here, Jim is the subject. Yes or no? When I come here, time step 0, Jim is the subject. Jim is the subject. Jim is the subject. Everywhere it is. In this one here, Jim. Tell me, engineer. Who is engineer? What is the subject here? Engineer. Who is engineer? What is the subject here? In the cell state at the subject place, what will be there? What will be considered as a subject? Jim only. He. Who is he here? Whom are we talking about? Who is the subject here? In the second sentence, Jim works for IT company. Who works for an IT company? Jim. Linda. Now the subject changes, isn't it? Does the subject change? Linda. As soon as you give Linda, the subject from Jim will be based on the historical data. The subject need to be now Linda. Jim will be erased. What is the subject? Is a teacher. Who is the teacher here? Who is teacher? Will it be Jim or Linda? Linda. Where does that change happen from the subject from here to here? The cell state got updated. The cell state got updated. The subject now will be Linda until we change the subject, isn't it? Okay. Let us see, to predict this one. To predict this one, what should be the next word? So by the time you reach here, what does the forget gate do? You know, what does the forget gate do? Based on the historical data, as soon as you see Linda, Jim will be erased. Jim will be erased. That's it. Forget gate will not update anything. It will just simply erase Jim. So right now, when you reach here, the subject is blank right now, null. That's what forget gate does. Okay. Input gate. Can you tell me what will input gate do in the subject box? What it will input gate will do right now? Based on the historical data, Zim will be erased. What input gate will do? It will now update. Forget gate doesn't have the ability. Check this out. Forget gate doesn't have the ability to write anything in the cell state. It just multiplies, which means whether you erase nothing, either you delete something or you don't delete something, but it doesn't have the ability to add. See, look at these signs. It is a plus sign here. It is a cross sign here. The plus sign will have the addition, which means here you add to the cell state after you erase something. You erased Zim, you add Linda to the subject. Linda, that is what input gate does. Output gate, you know what? When Linda came, here Linda is a teacher. Now when Linda is a subject, the output can be she, the output can be her, isn't it? The output can be Linda itself sometimes. Do you agree with that point? Output can be she, the output can be her, the output can be Linda. What should be the exact output? Who will decide that? That will be decided by the output gate. Output gate will decide based on the information of the cell state, based on the current cell state, based on the current cell state. The output gate will decide what should be the exact precise output. Because Linda was late that day, she can be one output. Linda's alarm goes off early, her can be one of output. Linda herself can be output. Do you agree with that point? Subject is this, but it can be any number. Depending on the previous historical data, output gate will decide. Maybe in this particular example, eventually, after going through all these historical examples, Linda is a teacher, maybe she will be the output. It all depends on the data. That is how LSTM works. How does LSTM work? It will have the cell state. This cell state is the one that will contribute to long-term memory. Short-term memory, anyway, RNN will take care of it. If there is an immediate dependency, RNN will take care of it. But long-term dependencies, okay, both Jim and Linda, if they are living in New York, then when we are talking something about New York, and very long back, there was a discussion related to New York, somewhere in the cell state, in some place, that city will also be stored. Like that, LSTM will work. Okay. That is a logic behind the LSTM gates. All these formulas put together, they will take care of the long-term dependencies. In fact, on a given data set, even you can even look back almost 1,000 time steps, because the cell state, it keeps on accumulating the information, it keeps on deleting the information. Forget gate keeps on deleting the unnecessary information. Input gate keeps on adding the necessary information. Output gate gives us the right information. Okay, that is the reason why LSTM works with long time steps. LSTM is one of the most advanced technique which works perfectly. Let us see an example. The previous example that we have seen is giving word 1 and word 2 as input, predicting word 3 as output. In this example, earlier we took words as input. In this example, we will take letters as input, characters. In word 1, character 2, character 3, character 4, character by character wise. In fact, do you know what? In reality, in our mobile phones, the previous example that I have shown you, do we give character level input or do we give word level input? Think about it. Do we type word by word or do we type one character and immediately we get the predictions, and this can will be considered as one word or can will be considered as three characters? If you check that in reality, just a second, yeah, if you check that in reality, if you say can, in reality can will be considered as three inputs, and then we have to the system has to predict the space. Then can space I will be considered as five inputs. In reality, it is the character level input that we give, it's not the word level input. And all these characters, one character by one character, even space is a character, we have to take all these as input, and our system has to predict next character. It has to predict a sequence of characters that will form a word, and then it has to predict as a word. That is what happens in reality, but RNN cannot do that much. Like if you go character by character level, even if you have two words, each of them having seven characters, 7 plus 7 plus space, you will have 15 time steps as input. Taking 15 time steps of input, would be very much difficult for RNN. Okay. So for RNN, if we are using character level prediction, we cannot use RNN. We have to use LSTM. Here is an example. In this example, what we are trying to do is we are specifically taking 14 we are specifically taking 14 characters as input, though they are two words only, but we are taking 14 characters as input, character by character level, and then after a space we need to predict next few characters that will form a word. That means we keep on predicting character, character, character until we hit a space, then we stop after that, and that will give us a word. Okay, that is the example that we are doing here. Since we are taking 14 time steps here, automatically RNN will fail. In that case, we have to use LSTM. Okay, let us do this example. So here is the text. This is just for the example sake. I'm considering this particular data set. Let us get this data set and then try to see few examples. All of you can do it along with me. So here are some of the examples. A calculation of, a catastrophe for, a celebration of, a celebration of. Like these are some of the examples that I'm printing. You can print more examples as well. I'm printing only first 300. 300 means 300 characters that I'm printing. Maybe you can print 300 to 1300 as well. When you print these many, you will see some more examples. Okay, a combination of a comfortable, like this. There are so many examples in this data. Here is the X data. Here we are taking 14 characters as input, and we are not only predicting the 15th character, we are predicting 15th, 16th, 17th, 18th, 19th, 20, like until we hit a space, until we create a word, we keep on predicting. And before that, we will take 14 characters as input. So basically the logic here is you first take 14 characters, predict the 15th character, and then you take these 14 characters, give that to the model, predict the next character. Like that, you keep on repeating it until you form a word. That itself will be challenging. Forming a word with the right spelling itself, that requires a good model. So here is the X data, and then the Y data is simple one character only. We have to do all that one hot encoding and all that. After doing all that one hot encoding, etc., etc., you will have this final X train, X test, Y train, Y test data. Here is the LSTM model. Okay, all of you, you need to understand the syntax of this LSTM model. Once we prepare the data taking 14 characters, obviously LSTM, the data shape will be how many our rows will be there, those rows. Then the columns will be 14 columns, and then each column how many ever one hot encoded. Earlier there were 139 one hot encoded. Since these are letters, maybe you have 24 letters and then special characters, etc., etc., roughly around 40 or something will be there. This will be the shape of the input data. Output will be single column, one column with these many one hot encoded values. Okay, LSTM sequential, model.lstm sequential. LSTM is the model name that I'm giving. Model.add, LSTM is a cell, 128 nodes, the number of hidden nodes in each of the cell. Input shape, as usual, input shape will contain number of time steps, which will be 14 time steps, and then the shape, one hot encoded values. And then final output layer, activation softmax, that is the LSTM. Obviously, LSTM will take a lot of time to execute because you have 128 nodes. That means forget gate node weights. You have uh, forget gate, output gate, input gate, all those weights, nearly 89,000 weights need to be calculated. We will try to compile this model. I'm running it only for one epoch. Rest of the epochs I have executed since it will take a lot of time. We will run one epoch, get the data, or get the model from my file. Later on, you can execute for more epochs as well, but directly you can get it from my previous execution, you can load this pre-trained model. After executing for one epoch, get the predictions. Okay, if the input is whatever day, then what should be the predicted value? If the input is knowledge and, then what should be the predicted value? So it will take KNOWLEDGE, knowledge. Okay, 9 characters. 10th character is space. 11th is and, 12, 13 is and. 14th character is again space. Like that, we give 14 inputs. You have to precisely give 14 inputs. You cannot give any word here. You have to, even if you are giving a word, make sure that you have 14 characters as input, because we are building the model for it, and then the model will predict the next ones. So I have executed for one epoch. After that, I am loading this pre-trained model that has been executed for multiple epochs, and then using this prediction to predict the next one. So whatever they, let us use this prediction. So if we are using this, let us see what are the predictions made by LSTM. So again, the same warning, whatever they want is a predicted value. These results are is a predicted value in accordance with knowledge and experience. Look at this, predicting next letter itself is very difficult, and predicting E followed by X followed by P, E, that means predicting with correct spelling and making sure that it is connected to this requires a lot of strength in the method that we are using. Since it is LSTM, it has long-term dependencies. Based on this, it is predicting knowledge and experience, political and economic. Remember, we are making character by character level of a particular interest. Now have you understood how this Gmail, how these mobile phones, we are getting right prediction? The models that are working behind the scenes are these sequential dependence models. These are the ones that will work on the sequential data, predict the next item in the sequence. That is the story of LSTM. Slightly very, what do you call, tedious or very much advanced version of RNN. Usually what people use, LSTM or RNN. If you ask me what people use usually, if it is a short-term dependency, when you are aware of it, then RNN works. It works as good as LSTM. But when you are sure it is long-term dependency, especially natural language generation, NLG, that means training something. In NLG, what happens is you, until now we predicted only one word, next word, let's say given 5 6 words, predicting the next word. What about after prediction of this word, taking this as input, predicting the next word, taking this as input, predicting the next word? If you keep on proceeding like this, that will generate some text, isn't it? It may not be meaningful, but if you train sufficiently, it can give meaningful text as well. That is known as natural language generation. In those tasks, we can use LSTMs. So we have to use LSTMs for capturing the long-term dependencies. For short-term, RNN works perfectly fine. That is the story of LSTM.